Okay, so normally this wasn't actually part of the lesson itself in terms of the book, but it's such a good problem because it's got so many little parts to it, and it does a really good job of reviewing everything that we've done in the last um, 3 sections that I have to do it. It's just a really good problem. Okay, so I'll give you a second to read it. This comes from the beginning of the book, actually. It was a case study about building better batteries. So the question is, are battery manufacturers constantly searching for ways to build long-lasting batteries? And so they take a random sample of 50 batteries, right? So there's 50 data points over here for that. And then they drained them under conditions that may make normal use. Here's the lifetime in hours of the batteries from one of the samples of 50 batteries that they took. Now, on the first one it says, make an appropriate graph to display the data sample, describe what you see. You are more than welcome to spend the time and actually punch all those numbers in. And what you would want to do, once you punch everything in, let me see, did I do it on mine already or no? Nope, I didn't. If you punch everything in, create a histogram for it, and basically describe what you see. So I'm being very nice to you, and I'm going to actually just show you what it should look like. Okay, it should look like that. All right, so the histogram is shown below. The distribution is roughly symmetric. Okay, roughly, not very, but roughly. With a mean somewhere around 16.718 hours and a standard deviation of 0.664 hours. They don't appear to be any outliers. And you get these two numbers by actually pressing on your calculator. All right, so that's pretty much what should go in this section right here where it says make an appropriate graph and then describe what you see. All right, so that's what it's supposed to look like. And there's the mean of 16.718 hours. I'm writing this down on other paper. And a standard deviation of 0.664 hours. All right. The next one, it says, assume that the battery production process, sorry, I'm reading up on this part. Assume that the battery production process is working properly. Describe the shape, center, and spread of the sampling distribution, which is basically what is up here in this section. Okay? The shape of it, okay, we'll talk about that in a second, because I want to write this down. What do I want to do? Is that number 2? Okay, yeah. Okay, assume that the battery production. So the shape, what do we have? Is approximately normal. Okay. Shape of sampling distribution, right? Not the sample distribution, because this right here is not really normal. Okay, that's just your histogram. All right, so the shape of a sampling distribution should be, sorry, I'm going to zoom out in a second. Okay, that's a little too much zoomed out. Okay, the sample mean, right, of what we have basically in what we got in number 1, is approximately normal. Okay, since, or because, the sample size is going to be greater than 30. Greater than or equal to 30, which is what one of the conditions was for the central limit theorem. Okay. In this case, the sample size is 50, right? So 50 is definitely going to be greater than or equal to 30. Okay, and then the mean of the sampling distribution is 17. or somewhere around 17. What did we get for? Yeah, the mean of x bar is going to equal the mean of what we originally had. So in this case, it's going to be 17 hours. Okay, since, and in this case, this works out really well. Okay. Since we're pretty much unbiased. Well, I don't know about unbiased. It's probably not unbiased in this case. But we'll see what happens. The mean is that one. And then your standard deviation is going to equal to standard deviation of what we got in the problem. Or up here, it's 0.8. That was our original mean. Divided by n. So we have 0.8 divided by square root of 50. So we should get something like 0.113. Since 50 less than 10% of our population means we need, what, 500? 1/10 of 500. And then, yeah. So we're good to go. So I'm pretty sure we have more than 500 batteries in our entire population of whatever, of batteries in this case. Okay. Okay. I think that's it. Describe the shape. Here's a shape. There's a center. Here's the spread, and then your shape. Sorry, I'm not being very organized today. 50 is less than, what does it say? 50 is less than 10% of all batteries produced. Okay. Alright. Here we go. Now it starts to get interesting. Number 16. Find the probability. It is simple. For a random sample of 55, the average life was 16.718, which is what we got on the other one. Find the probability of taking a random sample of 50 batteries with a mean lifetime of 16.718 hours or less. Okay. If the production process is working properly. Based on your answer, do you believe the process is working properly? Why not? Okay. So let's make the curve. We have 17, and our standard deviation was supposed to be, what is it? I'm looking at the other one, sorry. 0.113 is what we got. And because this is our sample, not the original. If we were just asking for one battery, then we would just basically go back to what we knew about the original, which was 17, and our standard deviation 0.8. But that's not the case here. So our standard deviation ended up being 0.113 from the sample. Okay. Okay. So we have 15. Okay, sorry. We want to know if it's at 16.718 and less. Okay, so this should go pretty quickly. So 16.718 minus 17 is 0.113. Z-score should give us, where's my work? I'm going to have to redo this, but I'm not sure. What is this, slide number 16? Slide number 16. Okay, so we get negative 2.50, and then this one we don't have to subtract from 1. So the probability of getting a z-score less than negative 2.50 should be equal to 0.0062. So basically, what is that, 0.6%? 0.6% chance. So less than 1%, that, what is it? That the mean of 50 batteries will be less than 16.718 hours. Okay, since the probability is so small, right, it is unlikely that what is it? It's unlikely that it's working correctly, I would assume. That the process is working correctly. Okay. So there's something wrong with the actual process of however it is that they're making these batteries. All right, 17 and 18. It's almost the same thing, except for number 17, we go back to what we did in section 7.2. And then we work off of that one. So a plant manager also wants to know what proportion P. Okay, so this comes from section 7.2. And in section 7.2, when we were doing the mean of P hat and the distribution of P hat, we had a little bit of a different formula for the standard deviation. The mean of P hat was still equal to P, if I remember correctly, and the standard deviation of P hat was equal to the square root of P times 1 minus P all over N. Okay, so the plant manager wants to know what proportion of all batteries produced that day lasted less than 16.5 hours, which he has declared unsuitable. For past experience, about 27% of batteries made at the plant are unsuitable. Okay, and then if the manager does not find convincing evidence that the proportion of unsuitable batteries P produced is greater than 0.27, the whole batch is going to ship to customers. So basically, we want to know. We actually want to do the shape, center, and the spread of the sampling distribution, and that is going to look like, well, where's my we're gonna talk about it, okay? Because I don't actually have a shape to actually show you, but we can talk about it. The shape should be approximately normal. Since the distribution of P hat is the same as P. Actually, no. I lied. That's not why. That goes for the center. Since N times P is greater than or equal to 10, and N times 1 minus P is also greater than or equal to 10. Okay, both of those are true. So 0.27 times, that's P. N is, what are we doing? 50 batteries times 50. So sorry, that's, in this case I did P times N. That's also going to be greater than 10. And 50 times 0.73 is also greater than or equal to 10. Okay, so the shape should be approximately normal. Your center, which is going to be equal to P, which in this case is going to be around 0.27%. All right, and your spread, or your standard deviation of P hat, is going to be the square root of 0.27, that's a 2, times 0.873, all divided by, what is it, 50? Yeah, we're dividing by 50. So it should be 0.0628, somewhere around there. There's a standard deviation. And then our 10% condition is met because, again, for the same reason that we did in the previous problem, 50 is less than 10% of all the batteries produced, if you can think of it that way. So I know that 50 is going to be less than or equal to 1/10 of my entire population. So my 10% condition is met. All right. Okay, and then 18, that's your shape, center, spread. So now we're going to use these numbers that we found, especially our standard deviation and our proportion, right, 27% or 0.27, to actually figure out what proportion of our sample is going to be less than 60.5 hours. Okay? Okay. Here we go. For the random sample of 50 batteries, the sample proportion lifetime less than 16.5 hours was 0.32. Okay, so the question is, find the probability of obtaining a random sample of 50 batteries in which 32% or more of the batteries are unsuitable if your P is really equal to 0.27. Show your work, and we should go by pretty quickly. There's our 0.27. We wanted to know more than 32. Our mean is the same as P. In this case, it's 27. Our standard deviation was equal to 0.0628. Okay, so 0.32 minus 0.27 divided by 0.06, the 6 to 8. So we have 0.80. Okay, so what's the proportion of Z being greater than 0.80? And in this case, you should get 0.2119. So the area under here is 0.2119. So that's about 21% chance. Okay, so there's about a 21% chance that a random sample of 50 batteries, okay, are going to be a sample of 50 batteries, okay, that sample proportion is going to be more than, that's going to last more than 16.5 hours, okay. Yeah, I think that's good. So since we didn't, what is it? Since there is about a 21% chance, that in a random sample of 50 batteries, 32% of or more would last less than 16.5 hours if the process is working correctly. Since in a random sample of 50 batteries, 32% or more would last less than, and that's an N, 16.5 hours. Okay. If the process is working correctly. Presumably. Working correctly. Okay, and so that's actually possible. 21% chance is actually pretty decent. So it's highly plausible that the process is, number one, working correctly, and number two, we got 32.32 by chance. So we're good to go. Alright, and that's it. Come to class, ready to do homework.